Hello and welcome everyone. Morning, good afternoon, good evening, wherever you are in the world. Thank you so much for joining us today. My name is Sarah Alspawn. I will be your webinar host. I am coming to you live from Cincinnati, Ohio, here in the US. As you most likely know, Siemens is a very global company, and we always love to hear where everyone is joining from. So feel free to say hello in the attendee chat and let us know your location. We also have a quick poll while we wait for everyone to join. If you don't mind, we'd love to know what brings you to this webinar today. I'll leave this up for about a minute while we wait for folks to join us here. But also, again, feel free to say hello in the attendee chat and let us know where you're joining from. And welcome to those of you just joining. Just doing a few housekeeping items before we get started with today's webinar. We'd love to know what brings you to the webinar today. You should see a poll up on your screen. Also, we'd love to know where you're joining from. Feel free to say hello in the attendee chat and let us know your location. All right, I see a few responses coming into the poll, so thank you to those of you who have already responded. For a few more seconds here, again, if you're just joining us, we'd love to know what brings you to the webinar today. We're going to go over a few housekeeping items, and we'll get started here in just a minute. Toronto, Canada, welcome. All right, so thank you for those poll responses. A few housekeeping items here, and then we'll get into the presentation. So at the bottom of your browser in the center of your screen, you will see icons in a widget dock, and these are the interactive tools that you can use throughout the webinar. You can minimize, maximize, and scale each widget to customize your viewing experience. I would like to call your attention to the Q&A Ask Questions widget that is open and located on the left-hand side of your screen. If you have any questions for the presenter, please type them in there at any time. It will look like your question disappears after you submit it, but we'll still see it fine on the back end, and we'll save those for our live Q&A at the end of the presentation. I think everyone has found the attendee chat, but if you're just joining, feel free to say hello in there. We'd love to know where you're joining from today. Also, I'd like to call your attention to the help widget that should be in the bottom of the widget dock. I think it's on the far right. If you have any difficulties, click on that, but do know that a quick refresh of your browser here in On24 will fix most issues, so definitely give that a try. Finally, this presentation is being recorded, and you'll receive a link to view it in a follow-up email. All right, a little bit about Siemens Digital Industries software. Siemens Digital Industries software helps organizations of all sizes digitally transform using software, hardware, and services from the Siemens Accelerator business platform. Siemens software and the comprehensive digital twin enable companies to optimize their design, engineering, and manufacturing processes to turn today's ideas into the sustainable products of the future. From chips to entire systems, from product to process across all industries, Siemens Digital Industries software accelerates transformation. All right, so into our presentation today, I'd like to welcome and introduce our speaker. With us, we have Matteo Girardi. You can read his bio in the bios widget on the left-hand side of the screen. Just click that little blue arrow to learn more and read about him at any time. However, I'm going to go ahead and turn things over. I don't want to take any more time away from his presentation. And attendees, just remember to put your questions into the Q&A, and I'll see you for our live Q&A at the end. So welcome, Matteo, turning things over, and you now have the floor.
Welcome, everyone, and thank you for joining today's Circuit Breaker Simulation webinar. My name is Matteo Girardi. I'm an application engineer at Siemens. And today I will lead you in this session where we'll explore how simulation technology is transforming the design and development of these devices. Whether you are an engineer, a product manager, are involved in R&D, you will see how Siemens integrated tools help tackle both engineering and business challenges. But first of all, who am I to talk about circuit breaker simulation? So let's start from the beginning. So after finishing my master's in computational mechanics in Italy, I joined the R&D simulation department of ABB, which is one of the most famous, as you may know, manufacturing companies for circuit breakers. My main job was regarding arc discharge simulation, but I was also involved in electromagnetic simulation, multi-body structure analysis. And then after a few years there, I moved to Siemens, where I am now, based in London. My main focus is on fluid and thermal simulations regarding electronics, cooling, electrical systems like circuit breakers, motors, electrical drives. And here I learned how Simcenter tools really step up the design and development of new generation circuit breakers. So today I will lead you through this session. So how to leverage simulation for designing new generation circuit breakers. Now we know that the electricity industry is evolving rapidly and circuit breaker design is more complex than ever. We need to ensure performance, reliability, safety, and efficiency while keeping the costs and time to market under control. Simulation plays a critical role in achieving these goals. With Siemens tools, we can predict performance, we can validate designs, and optimize engineering choices before building physical prototypes. By the end of this seminar, you will understand how Siemens solutions seamlessly integrate into development process, empowering teams to work faster and smarter. So today's agenda, what we will cover is, first of all, how do circuit breakers work? What are the market drivers and key industry trends? Then identify the engineering and business challenges, and then how these challenges are addressed by Simcenter tools, which are Siemens simulation tools. And then at the end, we will have a live Q&A session. So before diving into the solution, let's start with the fundamentals. So how do circuit breakers work? Their core circuit breakers are protection devices designed to interrupt electrical flow when a fault is detected. When I was working in ABB in my early days, my mentor used to say to me, Matteo, circuit breakers are nothing really so revolutionary. They are just extremely sophisticated mousetraps. And if you think about it, in fact, this is what they are. A device then, when triggered, in this case by an excess of current, it springs into action, cutting off power instead of a poor mouse and preventing damage. So let's break this process down further. So a circuit breaker provides a continuous conductive path in normal operation. So you can see here in the image, we have current coming in from here, from this terminal, then flowing into this helicoidal shape, which is the solenoid, the magnetic actuator, we will see later, then going into the mobile contact, flowing into the bimetallic lever, and then eventually going out. So normally, in normal operation, nothing happens, flow of current is detected into the circuit breaker. But when we have like overcurrents or short circuits, the circuit breaker needs to open and prevent damage. So this process involves a mechanical movement. You can see all these levers here, electrical contact separation, which we can see here, and then arc suppression. Each of this process presents unique engineering challenges. Then let's have a look at the trip system closely. So we have on the left the magneto trip system, which involved basically an actuator. We have a solenoid that basically generates a strong magnetic force that pushes this plunger to basically trip the whole system. And this happens instantaneously. This trip system intervenes when we have short circuit, so it's the most severe condition. On the right, we have the less severe condition, which is the thermal trip system, that basically gets triggered when we have overcurrents. So it means that current basically heats up this bimetallic lever that bends and strips the system over time, not instantaneously. So this dual mechanism ensures both delayed and immediate protection, making circuit breakers reliable and efficient. Now let's have a look closely at the arc suppression. So this is probably one of the most complicated on the engineering point of view physical phenomena. So when a circuit breaker interrupts a fault current, it must effectively handle and extinguish the resulting arc. So this arc forms as the breaker's contact separates. So you can see here in the image, now the electrical contact is separated. So there is a gap here. But basically, on short circuit condition, the current is so high that basically ionizes the air and creates a conductive plasma path, which we visualize with this little lightning. So we have the formation of the arc, and then electromagnetic forces basically stretch this arc and they push it towards this direction, towards this pack of metallic plates. This is called the splitter box. So you have the arc going down through the rails. And then what happens when the arc goes closer and closer to these metallic plates is that it splits into smaller arcs. And what happens when it splits is that basically each smaller arc segment encounter increased resistance, and the metallic plates absorb heat, cooling the arc and deionizing the air. So as the arc loses energy and the surrounding air regains its insulating properties, the arc is fully extinguished and it prevents any reignition. And without proper arc management, circuit breakers would experience excessive wear, material degradation, reduced performance. So it is a very, very important problem for circuit breakers. Now, after explaining more or less the behavior of this physical device, let's have a look at the market drivers. So a very important point is the electrification initiatives. Many developing countries are implementing electrification schemes to connect rural areas to the power grid, which is driving the adoption of circuit breakers. A second one is the aging electrical infrastructure, the need to upgrade and aging electrical infrastructure is creating a demand for new and more reliable circuit breakers. Rising electricity demand. As global electricity demand continues to rise, there is a growing need to reliable and secure power supply systems, which include circuit breakers. Then development of smart cities. The development of smart cities require advanced electrical system for efficient energy management and is also driving the market for circuit breakers. Environmental regulations, stringent environmental and safety regulation related to certain types of circuit breakers. An example is the SF6 circuit breakers. This is influencing the market dynamics for sure. And then the last one, the technological advancements. Innovations in circuit breaker technology, such as smart circuit breakers, electronic trip circuit breakers, are contributing to market growth. So these drivers are estimating to create a market size of around 30 billion by 2030. And this represents a strong compound annual growth rate, reflecting increasing demand across various sectors. So now let's identify the challenges that we are facing. So on one side, we have the business challenges. We have a rapidly growing market driven by growing need for reliable and secure power supply systems, as we saw before. Then we have costs that are constrained and reduced. So on one side, we have increasing in prototyping costs, but on the other side, we want to lower the development and testing costs. Then we have stringent industry standards. We want to ensure and performance while managing power density increase, packaging constraints, and need for cheaper cooling solutions. Then let's have a look at the technical challenges. So we have time scales for design and verification. We have manually intensive, limited automation, time to market is increasing. We have design exploration, so the ability to assess component troubleshooting and at the same time validate design changes at an early stage. And then cross-functional collaboration, so integration from CAD to multiphysics for digital democratization. Then on top of this, we have cost of switchgear failures. Failures in circuit breaker systems can be extremely costly because it involves deregulations, recall and repair expenses, and lost in market opportunity. So now let's have a look to a possible example of a simulation workflow. Of course, there are many. A simulation workflow that would aid the development of a new type of circuit breaker. So we start from the definition of our CAD system, our geometry, then study the thermal behavior, the electromagnetic losses. And then, of course, we have the study of the actuator, which is, as we remember from before, one of the most critical components because it allows the trip in case of short circuit. Then, of course, we have the multi-body analysis to be sure that all the levers, all the moving parts are moving properly. Then we have to verify, of course, that nothing breaks. So we have a structural analysis. And lastly, the so-called final monster, which is the arc discharge studies, which is, as we said, one of the most complicated problems to solve. And at the moment in the industry, the way of studying new circuit breakers with simulations is very fragmented. The problem is that all these analyses are so disconnected between each other, but the nature of the device is deeply interconnected. Especially nowadays with the trend of miniaturizations of circuit breakers, more and more all the different physics become intimately connected to each other, and therefore a proper digital twin is needed. I personally see a huge potential of Simcenter portfolio solution for this kind of products. So what if I told you that breaking the silos is actually possible? Having all these pieces of the puzzle put together in one simulation environment can be done in Simcenter simulation and test solutions. As we can see here, we have all the pieces of our simulation workflow done in the same environment, from the fluid dynamics, as we can see, the velocity, the fluid and solid temperatures. We have the arc discharge. We have the stresses and strain. We have the electromagnetic part with the losses and the forces and the voltage. A short circuit transient scenario. So all of these is possible to do inside Simcenter. But now let's have a look more closely and understand how Simcenter works. So Simcenter Simulation and Test is a platform that allows you to drive your productivity and empower innovation, exploiting our 4 pillars. So model the complexity, explore the possibilities, go faster, and stay integrated. So let's start from the integration part. The first important integration is regarding the CAD. So in Simcenter, we are always working inside a CAD environment. So we don't have to learn another graphic user interface. The way we interact with the model, with the geometry is always very familiar, in a familiar environment. A very important point is also that your analysis and your model are always synchronized, which means that any modification that you do on your CAD geometry reflects instantly on the analysis. And this is a very important point, allows you to bridge the gap between the design department and the analysis department. There is no geometry simplification required, or very, very little. So you don't waste time into the featuring, simplifying your geometry based on the type of analysis you do. And all of these benefits result in an increase of your productivity gain. Then let's move into the multiphysics integration. As we mentioned before, in Simcenter, you can integrate different kind of analysis. So, for example, the fluid and thermal, which is usually where we start with. We can analyze the velocity. We can analyze how the fluid and thermal temperatures affect your device. Example here. Then we can have co-simulations with the electromagnetic solver. So we can study how the electromagnetic losses increase the temperatures in your device. We can also study a very important part, which is the electromagnetic actuator. We mentioned it before. So here the challenge is modeling the transient behavior of this device. We're dealing with eddy currents, hysteresis losses. And here also another challenge is trying to integrate the electrical, the magnetic, and the mechanical aspect. Then we have the structural and multi-body solver. In this part, we want to study where the stress and strains concentrate. We want to protect these areas, avoiding any cracks or any breaking of our component. And then, of course, the multi-body part. So studying how the lever behave, especially now, as we mentioned before, due to miniaturization trends, these devices are becoming smaller and smaller. So we want to ensure that all the components are not clashing between each other, that the tolerances are respected. And here the challenge is, of course, high-speed motion dynamics. These components move extremely fast, especially in short-circuit scenarios. We have milliseconds as an order of magnitude of frame, and this requires precise calculations. Then let's move on to the model the complexity. As we mentioned earlier, we have the arc discharge, which is considered the final monster, so one of the most complicated physical phenomena appearing in our circuit breaker devices. As we can see here, the mobile contact is opening and the arc has been created and directed into the splitter box. This problem has a lot of challenges. With Siemens simulation tools, we can analyze the arc plasma behavior, so how the arc evolves and dissipates, the heat transfer and material stress, ensuring that the components withstand very high temperatures. In this kind of problems, we are talking about tens of thousands of Kelvin degrees. And then, of course, also the magnetic and the electric field interaction that is pushing the arc. We can analyze the data, for example, producing plots such as oscillograms, which are key plots to study the behavior in short circuits of our circuit breakers. Then let's move to the third pillar, the go faster. So for a standard combined flow and thermal simulation, we on a let's say simulation laptop, this was run on my laptop. It takes around 20 to 30 minutes. As we said before, the pre-processing time is actually very small thanks to the CAD integration and the robust mesher. So actually most of the time is required for solving. So it's machine time, is not man hours. And this enables rapid design iteration and optimization. So this opens the door to the fourth topic, the fourth pillar, which is explore the possibilities. Is if one simulation takes a reduced time, this means that we don't stop at one simulation, but we can explore, we can investigate a range of different configurations. So Simcenter allows you to do different kind of design explorations, a what-if analysis, which is a very simple parametric analysis where we manually compare different configurations. Then we can also do goal optimization, so we can find the best configuration. And then there are different kind of mathematical techniques to find the optimum. One is design of experiments, a very famous historical algorithm that generates matrix of optimal design points, and we can find the optimal one. And then finally, AI-infused optimization, so trying to find the optimum, use deep learning techniques. This allows engineers to quickly find in a very efficient and cost-effective way the best solution. Of course, having access directly into the CAD allows the engineer to change and manipulate the geometry in a very, very easy way. We work in parametric CAD, so it means that every quantity can be changed, everything else changes consequently. And this again creates a bond, a link between the design team and the analysis team. So now let's go back to our initial business and technical challenges. So business, the rapidly growing market. Now with simulation technology, it's possible to go faster to market because of integration, because of very robust measure and solver techniques and CAD embedding. Then costs are for sure reduced and constraints, since now prototyping and testing is not an activity that takes the whole design process, but only the last stage, and the rest is covered by simulation tools. Then the stringent industry standards, Siemens simulation tools are capable of reaching very deep levels of complexity that allow to fulfill the standards and be sure that the devices are performing as expected. And then on the technical side, design and verification timescales, as we said, with CAD embedding and the analysis being always synchronized with geometry, we start on an earlier stage to understand what's the best design. All the time that takes to continuously exchange, import and export is not there anymore. So we have way shorter timescales to get to the final best design. Then design exploration, we saw it the last slide. We are not just analyzing one configuration, even with the simulation, but we are exploring, investigating a range of simulations, a range of different configurations. And then cross-functional collaboration, whether you have only one simulation department doing all kind of analysis, or you have different departments, those can all be linked together to the same simulation model, and they can all talk to each other thanks to the high degree of integration of simulation tools. So this is the end of this webinar, and now let's open the floor to any possible question that come from the audience.
All right, my apologies, everyone. I was having some technical difficulties on the back end here, but we do have time for some Q&A. It froze up for Matteo and myself, so I'm trying to get Matteo back in here. Are you with us?
Yeah. Can you hear me?
All right, I can. Sorry, we had mine froze up as well, but we did get some questions here. Attendees, you can keep those coming in through the Q&A Ask Questions widget, and we'll get to as many of these as possible. Let's see here. What are the hardware requirements for running circuit breaker simulations efficiently, especially for complex multiphysics analysis?
Yeah. You hear me, right?
We can, yes.
Yeah, so it's quite a broad question. I would tend to usually split, when I usually talk about circuit breaker simulations, I usually split between two classes of problems. I would say, let's say one class is like all the, let's say, thermal, structural, electromagnetic, dynamic / multi-body simulation. That's one side. And the other side is the arc discharge. I would say the arc discharge is like a monster on its own. Is like, because there are a lot of physics all connected together, you cannot really decouple the phenomena. So I would say for those kind of simulations, we are talking about very heavy duty, let's say workstation or a cluster with, tens or hundreds of cores. For the rest, I would say using Simcenter and, its robust measures and solvers, you can, as I showed before, you can simply run on your laptop. Working on a CAD system, so you usually need relatively fast RAM. And then I would say no more than 20, 30 cores in terms of hardware. So yeah, I would say that's more or less the hardware requirements, depending on the problem.
Okay, great. Thank you. Our next question that came in, let's see. It reads, how scalable is this simulation solution? Can it be effectively used for both small-scale circuit breaker designs and large industrial systems with high voltage components?
Sarah, can you hear me?
I can. Can you hear me? Apologies, everyone. Looks like we're having some connection issue. It looks like we might have to answer some of these questions offline if we can't get Matteo's connection to reset here. Matteo, do you hear us?
I'll try to refresh.
So he's rejoining.
Can you hear me now?
I can, yes. So the last question I asked, I'll read that again. It says, how scalable is this simulation solution? Can it be effectively used for both small-scale circuit breaker designs and large industrial systems with high voltage components?
Yeah. So, the answer is like, can be effectively used for both? Absolutely, yes. So I would say, of course, Simcenter allows for parallelization, so let's say HPC options. So you can either, it really depends on the kind of physics you want to solve. Like even if you solve a very large, industrial high voltage circuit breaker, you might not want to study, the physics in detail. So it really depends on how much into the details you want to go. Simulating low voltage, very tiny, small, miniaturized circuit breakers, I needed to do, because the phenomena is quite complicated. But in general, yeah, 90% of Simcenter tools allow for HPC options. And then on the other side, I would say it doesn't really matter how big or how detailed is the system, since you are working inside the CAD, you're all integrated inside the CAD. The pre-processing capabilities are very robust, so you don't have to defeature too much. So on a small, low voltage circuit breaker or on a big one, you might think that on the big one you would have to spend more time in the pre-processing to defeature and make the geometry nice to be. But I would say always splitting between arc discharge and non-arc discharge simulation. For the non-arc discharge, you can just simply work on the original CAD, not waste too much time in the pre-process. It doesn't really matter the size. But when you want to do arc simulation, then that might change. So in that case, you might want to use a heavy-duty HPC. Yeah.
Okay.
I would say this is, more or less. I hope
Okay,
I had a question.
All right. Our next question here. Can Siemens simulation tools predict real-world failures or wear out mechanisms in circuit breakers?
Yeah, absolutely yes. And this is also quite a general question, but yes, of course, like there are, if you want to study, for example, fatigue-related failures, that's an option in our structural nonlinear. There are different mechanisms of, let's say, wearing out of a circuit breaker. So depending on the one you want to study, there are definitely options.
All right, and I think we have a few more here. Again, attendees, you can keep those questions coming in through the Q&A widget. And if we don't get to your question, we can always follow up with you offline. All right. Can designers or CAD engineers start performing simulation at an earlier stage?
That's a very good question. Really happy someone asked it because I think it's one of the, let's say, hot topic of the new generation of engineers. I remember when I was working in ABB, I mean, my microcosm is like a reflection of what happens in general is that you have usually like a CAD designer department. You design your beautiful circuit breaker. Then you have a simulation department. They live into different, like physically into different offices. Usually the CAD designers have interests that are completely different from the simulation analysts. And sometimes they clash. There is a big gap sometimes between the two departments. So more and more Siemens is trying to promote what we call simulation democratization. So bringing the simulation tools, not the tip of the pyramid of, let's say, a design process, but trying to bring it down closer to the base. The base is the CAD design of our devices. So definitely Simcenter being CAD embedded allows also CAD engineers that sometimes might be a performance simulations in a different environment with a physics that they might not be familiar with. In this case, you're working in an environment that is very familiar to you because it's the CAD environment. You know, you have full control of what you're doing. You're simply adding some analysis tools that are very user-friendly, designed in a very user-friendly way to allow you to start performance simulations. And by the result of the simulation, they can aid and assist your design. So we are trying to this gap between designers and analysts thinner and thinner. There are, automated workflows, pre-configured templates. What we know is that if you are a CAD designer for circuit breakers, you're not going to design automobiles or F1 cars. So you're pretty much always working on a very similar device, changing some levers, changing some bits. And for that, you can just, create a template that will always, be the same for different kind of devices with different kind of variations. You would have pretty much the same simulation set up. So you design it once and then you can use it forever so that you can, gain initial insights to the product performance just in a few clicks. And then, as I mentioned before, a very important point is that your CAD model and your simulation setup are which means that you, CAD designer, you get some insights from the performance of a simulation, then you modify your geometry, your CAD model, and that the simulation changes consequently. So there is never this, import, export, losing of information, losing of traceability between different versions, different designs. So this allows, to see instantly what impacts the performance and eliminate this bridge. Yeah, so it's more or less, I think it's anything I can say.
Okay, great. Thank you. I think that actually brings us to the end of our Q&A. Got to most of these questions here. If we weren't able to get to your question, we can follow up with you offline, but I think we got to most of these here. I would like to thank you so much, Matteo, for taking the time to answer these questions and, of course, presenting today. So thank you very much.
Thank you, Sarah, for assisting, and thank you, everyone, for joining.
Yes, we'd like to thank our attendees for joining us. If you think of any other questions, you can email me directly at sarah.alspa@siemens.com, and I can forward you on to Matteo, or point you in the right direction. And you can also put a question in there, and that will email me, and I can get you a response that way as well. Feel free to connect with me on LinkedIn. And this officially concludes our webinar. Thanks again for joining us, everyone. We hope you have a great rest of your day, and we'll see you around soon. Bye now.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.